lecture of the UVCE-ISRO Expert Lecture Series. Today is bound to be a very interesting lecture, and the lecture is titled Satellite-Based Navigation and Applications. And today we are joined by Dr. M Nageshwara Rao. I'm delighted to introduce the speaker to all of you today. Mr. M Nageshwara Rao graduated in M.Sc Physics, that is with a specialization in electronics, with a first rank from Andhra University, Vizag. Later, he did his PhD in physics in Sri Krishna Devaraya University, Anantpur. He joined ISRO in 1982 and was responsible for integration and testing of all the INSAT and GSAT satellites. He developed several software modules for the spacecraft integration activities. He was also involved in India's very first Space Capsule Recovery Experiment and contributed significantly. As the project director, he was responsible for the realization of NavIC Constellation Space Segment, and subsequently he was elevated to a senior management role in the ISRO Satellite Center as Deputy Director in spearheading various activities in spacecraft integration, spacecraft checkout, power systems, communication systems, and reliability areas. He then became the Associate Director of ISRO Satellite Center to oversee the realization of various satellite programs and their techno-administration. He was then moved to ISRO headquarters to streamline the realization of various satellite programs through policy formulation and coordination with different ISRO centers and functioned as the program manager. He retired from ISRO service in the year 2020 as a distinguished scientist after 38 years of service. For another year, ISRO made use of his technical expertise as a Professor Satish Dhawan scientist. Sir has also received numerous achievements and awards over the course of his career. 16 awards were given to him for his outstanding performance in M.Sc Physics. He has published over 35 technical papers in national and international journals, and he has authored many technical reports. He's also a life member of the Indian Science Congress, the Astronautical Society of India, and is an ASI gold medalist. Of course, keeping it short, his awards are numerous and many. So let us all give him a big round of applause and welcome him to the We are also delighted to be joined by Mr. Neelakandan, who is the coordinator for the UVCE-ISRO lecture series, as well as Mr. Prakash Rao, who has joined us. Both of them being very senior scientists from ISRO. Let us welcome them with a big round of applause as well. We also welcome the chairman of the Department of Electronics and Communication Engineering, Professor B.B. Harish. Kindly give him a big round of applause. Sir, you may proceed with the lecture.
Good afternoon, everybody. I want to thank Professor Harish and his colleagues for giving me a chance to interact with you people who are the future of India, and to share some of our knowledge, whatever we gained for the last 30 years. Because we are the future of this country, it is our duty to pass on whatever we learned to pass on to you, so that you will pick up from there and take it forward and you make it all this much more. And probably you would have seen, I think you are very young, when you are born you have just mobile phones are entered. So the mobile phones, the capability at that time, today you are seeing the change. Today I think whatever we think, everything we are able to do with that. You don't have to go to bank, you don't have to go to any newspaper, you don't have to buy anything you are able to do. So similarly, I am going to talk about the navigation satellite. Most probably all of you are heard about GPS, and we it's taking you to new places or new homes with the help of GPS. So, but I don't know how many of you are aware what is the technology behind it, how the GPS, the Global Positioning Satellite System, is helping you to do this job. I don't know, because some of you are definitely, with your own enthusiasm, you would have learned. If not so, today let us see what is that we are trying to do, what are the various constellations world existing today for doing the navigation business, and what is that we are trying to do in India, and what is that future we are going to work in, so that we are all going to be part of that system, taking the systems what we are today having to much higher levels. Shall we start? The presentation is visible to all of you.
Yes.
Some seats are vacant, maybe last seats are unable, so you can come to front. So it's up to you. So it's a very tough time. Generally after lunch, especially when we have become old, we try to have a nap. But keeping you awake is also going to be a very tough time. Let us see that how do I succeed in doing that. Okay? Okay, now every country when they are having their own space program, they have a specific goal, what they want to do it, what that country deserves, what is the socio-economic conditions of that particular country, what they are trying to extract from the space. But in ISRO we started, India we started, government started, our leaders started like Vikram Sarabhai. They have a specific goals that they want to do to the space. So ISRO has started making some difference they want to make in the space, and they don't want to go too much behind what's happening in the department of space utility everywhere. So they want to have a scientific pursuit for the applications of space with a lot of common sense and a little bit of engineering what is available in the country. So this is the space our forefathers thought we should do, ultimately leading to socio-economic development of the country. Take the benefits of the space to the common man. Probably you heard earlier lectures, some amount of idea you got it. Each of the field, remote sensing or the communications or the applications, what Nilakanta talked or the Seturaman talked you or the Ravu talked you, got some idea. And now I am going to talk something else later entry into this. So there is a mandate from United Nations also that we should ultimately aim at taking up the socio-economic development of the people of the country. So we are in tune with United Nations requirement. So that's why Department of Space is working for that. So oh, sorry. I didn't see that. Okay. Otherwise, that's you manage. Okay. So what? Yeah. So to whatever I talked in the first slide, to do that, what are the things we need to put into the realization? So we need basically a space segment to do certain activities. So we talked about the Earth observations, the communications. You heard something and you are going to listen some more things, and the navigation. Already we are into the space science. To do all this, we need some sort of ground segment to help the satellite and to bring what's happening in the satellite or to have a contact with the satellite. We need a good amount of ground segment. And to put these satellites into orbit, we also need quite good amount of rockets with variable capabilities. So to meet that, we have the Polar Satellite Launch Vehicle, we have the GSLV Mark II and Mark III, and we are now going to, of course, we had one launch and we are going to have a subsequent launch of small satellite launch vehicle. Also, we are having a reusable launch vehicle like a space shuttle what we have done. So these are the things to put these satellites into operations. And then we need from this what we are trying to achieve. We are trying to achieve socio-economic security, sustainable development of the people, and the disaster risk reduction techniques we are going to provide to this whatever the satellites are putting. and e-governance. Today you are seeing a lot of things are happening. You don't have to move the papers. So physically, so many things happen. You go to a particular place, a click of a mouse button is appearing everywhere. So e-governance is happening, and probably I don't know how many of you are having your credit or debit cards with you. And when earlier days, sorry, how much time you can this for?
2 hours.
2 hours. That means 5:30. No, because I need to moderate tonight. Okay, we try to do that. And probably you would have earlier when we are things we started, we want to go on holidays or we want to go to native place, from place to place. We need to plan how many days are going off, what is the type of amount of money we need. Go to a bank, write a big slip, take it, all that we need to do it. Today you don't have to do that. If somebody calls, you get a call, put your card in the pocket, start moving. On the way, everywhere you find your metro station, you find a ATM booth. But how many of you are? What is the system that is making it so easy, and how the systems are interconnected? So this is the satellite sitting there is providing a facilitating this whole of your transactions from your main machine to your centralized bank or to your local bank, getting into your account and allowing you or not allowing you to withdraw or do some transactions. So these are all things we are trying to do to the e-governance. That is as simple as that. And then we are to do this. What are the things we need to? We need to have a lot of human resources. That's why all these education institutions are UVCE, Electronics and Communication Department. So we need a good amount of human resources for this, and we need a good amount of technical infrastructure like whatever the satellite centers, rocket launch centers, application ground stations we are putting, and enhanced throughput we should create, and continuously we should bring in new technologies. Otherwise we will be left in the technology in the world. So you cannot afford to do that. You should continuously bring new technologies, and you need to do international cooperations. So like what we did in the American very much aware, we have like the South Asian satellite, where the satellite we are doing the space diplomacy. And the last flight of PSN we had the proton sat, where we are cooperating with them and doing that. So we need to do that type of international cooperation, and I think project director was the Prakash for the Asia South Asian satellite. Made the satellite, and then we need to have the outreach activities. So probably this is what we are trying to do as part of outreach. Go to you and talk to you and say that what are the benefits that we are going to get, and attract you towards the space. Next slide, please. So today we have completed most of the things, and we are going to some of the things. We are at navigation. Today I am going to talk about some of the concepts of navigation. I don't know how much I will succeed. Definitely I will try to do something, and you people will try to understand what is the something like. Because this gentleman, so many people need to talk when you come to the navigation systems. And somebody will be talking VAS, GPS block 3, block 2, block 1, and somebody will be talking GLONASS, GLONASS M and GLONASS Satellite. Next somebody will be talking about the Galileo or Network systems. Somebody will be talking about the compass and blue systems. And somebody will be talking about the SEMSAS and the QZSS. I will tell you later. And IRSS, Garden and SPS, Satellite Position System, Satellite Navigation. And because all these systems will be, the heart around this is the atomic clock, the augmentation of the signals. And then somebody will talking about the DOP, dilution of position and DVR, things like these are all confusing words. The people are confused so much. So, wondering what is all this? So I think I will try to, at least some of the things I will try to make it familiar to you, so that you will not have confusion like this, a confused man. So you will have clarity and you will understand what are these terms in terms of the navigation. Why your navigation is required? So are you lost? Now you assume you are someplace in a deep jungle, or you are on a desert, or in a deep sea. Anywhere you look alike, but you don't know where you are, and you want to go, you don't know where to proceed. So you are here, it says board says, but where you are here, you don't know. So no guidance. Now you are somebody in the space, and there also he says about you are here, but you don't know what height he is, which latitude, longitude he is, he doesn't know. So no references are available for him to say that where he is. Next. So in that type of situations, you need a navigation. So navigation is the rescue for you, because the navigation signal should be available to you to know that. And I cannot say only Bangalore, if I get back, you are in Bangalore, it works, and tomorrow you go to Hyderabad or Delhi, you are lost. Cannot be like that. I need a navigation to rescue everyone. Okay, next go to this. So omnipresent map. You say everywhere you are here. So you say that you are lost. You don't know where you are. So navigation at your rescue. Next. Now assume, of course, even you today Bangalore, some of the flyovers you see also, it is as complicated as this. May not be so much, but as complicated as this. Look at this particular top line interchange Atlanta, Georgia, and there are so many intersections you are seeing. Even you have gone there to study or to work, you have taken the car, but let us assume you don't have the GPS, and you have to take a turn and go, and you are lost. You don't know, you stop the car and wait, or somebody has to guide you. So assume you are going to have such a complicated intersections. You need some guidance. So how we are going to provide? So the same thing, whatever the maps I showed, the physical thing is the Google or GPS is converted to this map, and you know that when you are moving, you know that on your screen you will be getting take left, right, first exit, third exit, fourth exit, like that. You will be getting a voice announcements also. So this is the GPS aided navigation map. So navigation, why we do navigation? Basically either the space based, the navigation, or the ground based, or any navigation we will need. Don't we want to know where we are and which way we are heading? So definitely we want to know. When we are coming from ISRO to UVCE, air conductor was explaining to the driver, take left, take right, go to circle, and first right you take, and go to U-turn, all that I was telling. And instead, I put a map, the driver is conversant with that, leave it, car will come here. So, of course, yes, in a more technical sense to know where we are is nothing but position determination. And once you know the position you know, then you are moving. You can, with respect to time, you can say that how much you are moving, and you can calculate your dV by dt. And if you want acceleration, you are this way, v by dt square, you can do it. All that you know. First you should know the position. And position is changing, you are moving. If you are not moving, position is zero. Moving is zero. So this is determined by defining the technical terms, the latitude, longitude, and altitude in a particular time frame on the Earth surface. Correct? So these three parameters you know, you can define clearly where you are. You are in the sitting in the UVCE or any other results, also you can clearly tell. Using this piece of information at determined position for monitoring and controlling the motion of a craft is called the navigation. It could be a craft, it could be a man, it could be a car, anything. So using this you are moving, it's called navigation. Next. So now what are the three? As I told, we need a latitude information because you are at some height, your aircraft, you should know what height you are. And you should know that. And the longitude, latitude is longitude, the position in the earth if you globe if you put, so you know your position. Then elevation also you know, we are at not on the surface. Then also you need very very important to you want to calculate your velocity or acceleration, you need the time also. So we need 4 parameters to define exactly where you are. So now you have the shot with all this provided with the x, y, z and the time. You can determine your position without worrying if any of the references. You can keep moving and decide where you are. Next, I want to, in simple example, I want to just tell you how do we do the fixing the position fixing we do. Somebody has lost, he is in somewhere, he lost, he wants to know where he is. So he called somebody, his friend, and asked him, can you tell where I am? So he told, you are 300 km from Bangalore in Karnataka, he told. He answered that, then what happens? With that, he can next. So with that he can draw a circle with that from his location with 337 kilometers radius, and he could be anywhere within that. Still it's a very big area, he doesn't know what it is. So it's confusing. So next. So he calls one more friend and says that, could you please tell me where I am? So he says, you are 416 kilometers from Devaraya, Kerala. So now what he says is, from that location, so around Devaraya, he draws another circle. Now these two circles are intersecting somewhere. So that means most of the area you eliminated, you are coming somewhere in the intersection zone, you are there, but still you are not very sure. That area could be very large. So you don't know where you are. Now I want to know where I am. Next. And he calls one more friend next. Okay, he calls one more friend and asks where I am. He says, you are 150 kilometers from Vizag in Tamil Nadu, and with that he draws another circle. These three circles will intersect one place. So that means you are there. So this particular technique is called triangulation. You know the some coordinates. You can draw like this, and you can fix your position. Now, because these are all land, somebody should know exactly to tell the trigger because it's easy for you explanation. I have taken an example, but it's very difficult because you don't know where the person is. So how do you do it? I want to do it with the satellite because it's not possible on the ground. Now how do I do it? Go to next. So more references if I get, I will be refining my position exactly where I am. So that's what it says next. Now from the triangulation I want to go to three-dimensional, it's called iteration. So I am going to do the space I am going to take, not on the surface, it's not a two-dimensional anymore. I am going to three-dimensional. So similar to 2D, iteration just is a bit trickier, but we can do it. The area from the previous example to go off in all directions, you will get a series of spheres. Instead of the circle, you get a spheres. So if you know 100 kilometers from satellite A and all this, I will show the example. Go to next slide, please. Next. Now I have a satellite A in space. Next. Satellite B. Next I have one more satellite, satellite C. So now these all the satellite signals are coming, and you are sitting on a receiver, electronic receiver, standing there and receiving the signals. How do you, now I'll tell you how to do it further. And with this interaction, it could be either Q or P. Next. And you don't know where we are. So now there is air. The signals you are receiving on air. P is an imaginary. Now we are at the P. So from these, you can measure and fix your position. You are at P on the surface of the air. So each itself is a fourth sphere, and the parent P which is on the surface of this sphere is the solution. Next. Now I have a fourth satellite, satellite D. Next. So now earlier we talked about we need 4 parameters. I need X, Y, Z, and the time. There are 4 unknowns. I have the 4 set of information is coming. By manipulating these numbers from the 4 satellites, I can fix my 4 unknowns. How I am going to do it, I will explain to you in the coming slides. Next. So as I told earlier, more satellite means gives more accuracy. That also we see how more accuracy will come. Then as I told in the previous slides I was telling, we have the Ajanta watch, that watch, this watch, and the Apple watch, the costly watch. So but we are not happy with that. But today time is maintained by one of the mechanical watches. It's maintained by the atomic clocks. So what you are talking is atomic transitions with the angstrom level you are talking. So that's how the clocks are maintained, and that's why I want to tell you the navigation you talked about using the atomic clocks. Why do we need atomic clocks? Why not the Ajanta clock? So we explain that satellite navigation revolves around the time. The basis of satellite navigation is the distance is the time. I am going to show how it is. Distance equal to, you have the propagation rate is there, and it has taken a certain amount of time. The propagation rate is the time, if you multiply, you get the distance. You are going in 4 km per hour speed, and you took 2 hours. That means how much time you travel? 8 kilometers. So for that, you know the time and the rate, you can know what distance you are traveling. Propagation rate is speed of light, because that's any electromagnetic wave. If you are traveling at the speed of light, that is 3 × 10⁻⁸ meters per second, right? So So that parameter is fixed because that number is very big. You look at the 3 lakh kilometers per second is the speed of the light. So time taken from the signal to propagate from the space vehicle to the receiver is very precisely you need to measure, because that number we are going to multiply with a very big number of 3 lakh kilometers per second. Any small mistakes in the time, it will result in a big error. So now we have the satellite, but now I have a satellite. Okay, I have a satellite. Basically, I have a receiver. Today I receive nothing but your mobile or my watch, Apple Watch. So morning I go for walk. I don't have mobile, but my watch will be there. This fellow I will keep on tracking. When I go home, the data will be transferred from this to the mobile. I can, my wife can take the mobile phone and see which are the places I was morning for walk. And what speed, what is the heart rate, all that it will tell. So that is the technology. What is the receiver we are talking is the mobile phone, or it could be some other device sitting in a bus or the car or in a railway bogie. Next please. Next. Okay, how do I measure the time? Whatever I thought, the precisely need to measure time. The PRN, pseudo-random noise code is sent by a satellite and also generated by the receivers. Both will be, we have the same set of codes, they will be running concurrently. And the code from satellite reaches the receiver. The time difference between the code receiver and code generated by receiver is what propagation time. That is C into T propagation. Now I have pointer. It's okay. Then the satellite signal is coming. I am running a same PRN sequence from the ground, pseudo-random signal, nice signal. And both, if I compare the satellite coming signal and my receiver, I know how much time the signal has taken to reach from satellite to my receiver. So that I multiply with the speed of light, I will get the distance. Correct? So now, that's why the whole satellite, so today we have GPS, have their own set of time standard. And the GPS receiver will have the references. And if our IRSs we are talking, we have our own time generation. So Indian time reference we say, they will compare and we can calculate the distance. Next. Now just I will explain with your own known equations of the signals, how the time delay is explained. So now you have to use RF carrier coming from the satellite. Next. On that I have a PRS sequence and I modulate the PRS sequence on the calculator. So this is my PRS sequence. If I modulate, I will get a modulated RF carrier. Because many communication you want to do, you need a carrier and modulation signal. I will do that. So my modulated signal will look like that. And then the satellite transmits the signal, I will receive at the receiver. Then I reproduce, I take out the RF carrier and get back my PRS sequence. If I get back, if I know this, the difference between the satellite transmitted, the ground receiver, this is the delay, that much time it has taken the signal to reach from the satellite to the ground. If I multiply the time with the speed of light, I will get the satellite distance. Next please. Now let us look at it. Somewhere I am on the ground, I don't know where I am. I want to know my x, y, z and t. How do I do it? Next. I have 3 satellites in the space. Yes. I have x1, y1, z1. That means, how do you know that x1, y1, z1? We have a satellite also, we call what we do is the ranging to the satellite. Probably you would have heard in earlier lectures. So we send a signal and we get back and we say that satellite is a particular height and this is the coordinates like that we define it, longitude. All that we do it and that x1, y1, z1 of each satellite will be fixing it and we will be transmitting the whatever the data set we are transmitting from the navigation satellite. So for the second satellite I have x2 and z2, third satellite x3 and z3. Now from these I receive it at the ground with the receiver and I calculate my tau1 and multiply with c, I will get the satellite distance 1. Then I will get complete satellite distance 2, satellite 2 distance 2, satellite 3 distance 3 I will compute. Next, wait. So now I have 3 equations and I have 3 unknowns. You have simple geometrical mathematics you would have learned. I have 2 points x1 and x2, x1 y1, x2 y2. I want to know the distance. This is the equation, right? x1 minus x whole square plus y1 minus y2 on the square root. You will get the distance. Correct? I have the 3 here. This is the equation. I have exact NSX, y minus I varying 1, 2, 3 satellites. I have 3 unknowns, 3 equations. If I solve that, I will get my XYZ. As simple as that. Nothing great. The simple mathematics. What we learned in the 10th class. Next. Now signal is transmitted by the satellite. Now I receive the signal from at my receiver, a particular satellite. All the satellites will be transmitting. My receivers will have like your radio receiver will have my radio receiver has got 10 channels. I can receive medium wave, SW1, SW2 like that, or FM1, FM2. Because the receiver has got a multi-channel receiver. That means it can receive so many satellite signals simultaneously. And internally we will be computing all these computations we will be doing. Next. So now I have a one more satellite, fourth satellite telling it is at X4, Y4, Z4 and its distance is D4. I can extend my previous 3 unknown equations to 4th unknown equations. Here xi, yi same equations with I varying from 1, 2, 3, 4. So I got the time also. With this I am going to get x, y, z and time information. So whatever the t-shirt we saw that to move yourself independent of any references. Now with this, the 4 satellites transmitting signals from the space, the receiver can pick it up. I am getting all my 4 unknowns and I am ready to move without any reference, whether it is a Chennai or Bangalore or Hyderabad or in Melbourne or in New York. It doesn't matter. The 4 satellites are available to me. 4 signals are coming. I can use mapping of these equations. Thanks to Google, there are Google Maps. These are put on the Google Map. That's how you are moving. The car shows it's moving. You book Ola cab also, you see Ola cab is taking 1 minute to move it. So that's how it's done. Next. So that means minimum 4 satellites are required. Because you have 4 numbers, you want to solve 4 equations, 4 satellites are required. Yes. Now how do you do it? Basically, this, as I told, the pseudo-random numbers will be generated on board. The signals are modulated and getting a RF carrier and remote. Next, what I am going to do is, I am going to do this manipulation in my mobile receiver or any GPS receiver or any NavIC receiver. I am going to adjust. I am going to measure this TM. So if I measure the TM, next. So how do I do it? Now, as I told, we say 8 channel receiver or 10 channel receiver. That means satellite information is taking. So I do an auto correlation. Correlation of signals are between because each satellite has got a unique appearance sequence. Otherwise, you get confused. So satellite, once I know the appearance sequence, I can correlate my receiver appearance sequence, free sequence what I am running. I can check the satellite number 1 is coming, or 2 is coming, 3 are coming, 4 are coming. All that I know. So I will do the auto correlation. Next. So this is what is happening in your GPS, your mobile without your knowledge. So the correlate will be running with pair input matching. Whenever the 2 ports are matches, you see that all will become green here. So that means there is a correct sequence, that is the satellite we are getting, and that particular satellite data, the FMNS data or its D1, whatever we found, or XYZ, all that we need to pick it up from that and start making with that. So this is how internally is happening. The correlation and fix the satellite position. Take that particular satellite. Now you identify the satellite is coming. You pick up that FMNS information and start processing and your position will fix it. Next please. Okay, now having got that, why I need high accurate time? Why not Azinta clock or any other slightly better clock? Means navigation satellite employs very high precision clocks called atomic clocks. Some are earlier started using the cesium clocks. And now we have got a rubidium clock. And even hydrogen majors are there, they are very heavy. They are all used on the ground. And across the board, many of the hydrogen majors and cesium clocks are ensembles are made. All this information is derived today at central locations. They call it universal time to generate from all these atomic transitions, not from any other clock movement or spring movements or anything. The typical axis of some atomic clocks are hydrogen clock. The hydrogen major, what I say, the variation is 1 × 10⁻⁻15 seconds per day. It's a very bulky. And cesium clock variation 1 × 10⁻14 seconds per day. This is also bulky. And rubidium clock variation 1 × 10⁻13 seconds per day. It's a lightweight. This is what everywhere the navigation satellites are using, including our ISRO satellite, what we are using. 3.2 kgs atomic clock we are using with the rubidium physics package of 1 inch by 1 inch, 1 inch, all the transitions I will show you how it's going to be. The ratio can be error in measurement of 10 nanoseconds. The 10 nanoseconds error if you make a measurement, your position estimate is going to do 3 meters error. Hence there is need for very precise and accurate time measurement so that you don't get into the big error numbers. So that is important of highly precise clock requirement on board the navigation satellites especially. Next one. Okay, go ahead. Now I have 4 satellites here. And let us assume each satellite has a computation of some magnets. Some magnets. Next. So one satellite has got 8 nanoseconds, one satellite 9 nanoseconds error in the determinations. With that, so you will be in this type of whatever I showed earlier, the first thing, you will be getting into that. So your position is going to be vague, you are not going to be precise. I want more precise position, I need more accurate timing because I am multiplying with a big number, that is the light of the speed of the light. Okay? Next, go to the next slide. So, okay, now we will, second is actually referred to as atomic second now. This is why the connected to the second. But what is second is defined today. I don't know, some of you are aware, otherwise this is the definition. The interval of time taken to complete this many oscillations of the cesium-133 atom exposed to suitable excitation. So this is called the atomic second. This many translucent has to take place from the atomic level. You would have studied the chemistry, right? Atomic numbers. The hydrogen atomic number is 1. It has got a nucleus and it's one electron moving in the 1s state. Helium 2 electrons. Next you go to lithium, beryllium, boron, carbon, nitrogen, all that. So number of electrons are moving. You have the 1s, 2s, 2p, 2d like that. So it's going moving around your nucleus. So that's where one state to other state, because they are taking the electron from one state to other state. From 2s to 3s if I take it, that's the atomic transition. That is the rubidium, the relation between the atom and the time versus the requirement of the atomic clocks. So these are the atomic clocks are big. Next please. Now, because we said that exactly not only the timing computation, there are other means of getting into some errors in your position fixing. Let us look at it. What is those numbers? So you have the satellite, you will be coming, you have the receiver or your mobile, and it's a reflection of the signal. It's an RF signal basically, right? Whenever it is impedance mismatch, if you see, it will reflect. The ground it reflect. So you have something received like this, a reflected signal can hit your rooftop and receive your GPS antenna, whatever you can watch. Or it can directly receive signals, and the third signal is reflecting from the ground and receiving. So there are 3 things are coming, you will get confused and you will sometimes get into the loop. Exactly you are not able to determine what position you are. Use multi-port reflection receivers, and one more thing is the signals are coming from the space. I am going to talk about various constellation skies, but they are going to come to the atmosphere, more so at your troposphere, ionosphere and all. Where these frequencies, what we are talking L1, L2 or S-band, they are supposed to going to be slow down the waves, and depending on the ionospheric condition, the numbers are going to vary. So if you don't know what is the particular time, the activity of the ionosphere, this position is going to be inaccurate. So we need to compensate that. So all these are going to manifest into error computation errors. Next. So what are the various errors can be pseudo-ranging errors? Why I say pseudo-ranging error means I told if you want to know the satellite, you have x1, y1, z1. I need to precisely tell what is my x1, y1, z1. If I make a mistake there and my computation is going to be because your I minus x is there, x is wrong, your xi will be wrong. So I need to precisely, the pseudo-ranging errors are going to be guide my position of the spacecraft. Then influence on the GPS signal, somewhere radar signals are coming in the same frequency band, it is interfering, and some microwaves near the airports will have the same similar type of thing for that aircraft landing, they have automatic landing equipments, they will be interfering, and the radios and ATC radio craft signals also interfering, so they contribute some sort of mismatch in the computation. Errors to multi-path reflections, ground plane and antenna to eliminate the ground reflections. Move away from the reflector surfaces is not possible anymore, you can tell that. And because wherever you are there, you should be able to estimate, you cannot lose. Misidentification of threshold and other features. So these are all some of the things errors comes. So how do you define the errors? Ionosphere errors, we contribute plus minus 5 meters. And ephemeris errors could be 2 meters. Satellite positioning we are able to do more accurately and tell that will lead plus minus 2.5 meters. Clock errors will be plus minus 2 meters. Clock also will have a variations, jumps. Multipath distortion plus or minus 1 meter. Troposphere will be contributing plus minus 0.5 meter. Numerical errors in the computation, your algorithms can contribute to plus minus 1 meter. Altogether. So these are the various sources of the computation errors. Now, one of the important factor for position fixing is we call it the dilution of precision. By precision, how much is getting diluted. So I will try to explain with a simple examples. So how that's why where we get into the satellite constellation frame design. Somebody will say 30 satellites, we say that 7 satellites, somebody says 29 satellites, 27 satellites. All that is decided by what is the type of dilution of precision I want to provide, how best accurate signals I want to provide. This is how we will do it. Let us say now the first example I told, I will have next. So I am doing ranging from Mumbai. So I made a small mistake of plus minus time. So I could be within the two upper and lower dashed lines. My exact location is the continuous line. Let us say I do the ranging from Devaraya, which is in Orissa. One is on the west coast, one is on the east coast. If I do a ranging from this, and I will get into my both errors are same, I get into the position ambiguity. Next. Into this white shaded area. So, because of the computation timing error, I could be within this. Let us see that how this is going to change depending on my ranging stations. One is Mumbai East West I have taken. Let us I consider some other place. What is going to happen? Now go to next. Now same map, same outcome I want to do it. Next. So next. Now I am doing instead of Orissa, Bhubaneswar I want to Madhya Pradesh, Raipur. Next. Next Bhubaneswar I am doing because there are two close by stations. I do it. Now look at the same errors I am making like previous. Now what's going to happen next? So now the white thing shows that your error is this. So this is called dilution of precision. So that means from where how apart I am doing the ranging, it matters. So that's why when the satellites are there, where to put my satellites to have a minimum dilution of precision. The maximum DOP number means you are going to get into the error, more error. I want to minimize this. Next. Okay, similarly, this is how we need to minimize. My sources should be such that I will minimize these numbers. So from this it is evident that the reference stations, the person's precision of location is less diluted in case 1 compared to case 2 because the stations are very far and in this case the stations are nearby. So this is applicable location of satellites in constellation, in orbit. If somebody says that I have 55 degrees inclination on a particular 19,000 kilometers, somebody says 21,000 kilometers, somebody says 27,000 kilometers. In IR navigation we say we are at 6,000 kilometers. These are all meant for the constellation design. And I need a target, what is the accuracy I want to provide and now to match that I need to design satellite positions so that I will be getting into this type of dilution of precision. Next. So now how do I define or accept or reject the dot numbers? Satellites will be, even you take a receivers and satellite 12 channels, 13 channels cycle, that means satellites will be coming. Some of the satellites the top will be very poor because the satellite is your head above or very far. And we say that very good doubt number if it is between 1 and 3, there is no question on 1 to 3, and good we say 4 to 5, and fail if it is 6, and if it is greater than 6, we suspect and drop the signal. We don't take into consideration because we lead to the wrong position computation. So RM position error is RMS range error and division operation. So that is directly going to impact your position fixing. So mission planning is very critical for obtaining a good draw. So when we design our sun satellite navigation constellation, we have run thousands of equations to get what should be the satellite location, where should be there, and over India we want to have throughout a good directional operations, what should be the thing we calculate. So now let us see that what are the various systems are available in this whole thing. Americans are leading from the, because all you people are familiar with GPS only, because you know me in GPS, other things I don't know how many of you are aware of that. But GPS is the American. So they started somewhere in 1960, 76, by 1982 they brought a good number of satellites into orbit, and they started using, and 1982, if I remember correctly, so there is a Korean aircraft coming from the US to the South Korea and is overflying Russia. So there was a problem with the onboard gyroscope because satellite aircraft is guided by the gyroscope. Gyroscope problem, it is deviated from its path and has started going over Russia, and they are not having information. And the Russians started interacting with the civilian aircraft, and they are talking, but because of the language problem, the pilot is not able to communicate. They are having a problem with onboard the gyroscope, and they thought that some enemy is coming. The Russians fighter aeroplanes are gone and shot the passenger aircraft. Near 380 people simply exploded. And after being shot, and the US president has got a presidential declaration that GPS signals will be available to please start using. They started putting ICDs, that is the interface control documents are put on the made available. People started receiving and told this will not be disturbed and people can use it so that any error will not get into that type of disaster. So they are the first to start. Then you know that there is a Cold War in 1960s, 50s between Russia and America. Whatever America is doing, Russia cannot keep quiet, Russia is doing, America cannot keep quiet. So when they are building American systems, so they thought, we also should build our own system. They started known as Global Navigation Satellite. GPS is Global Positioning System. Known as the Global Navigation Satellite System by Russians. And Galileo also, they started Europeans. Yes, we should have, we are strong in the world. We also should have our own navigation system. We should not depend either on the GPS or the GLONASS. They started their own Galileo system. And any Chinese cannot keep quiet. They are trying to lead the world. And they started their own system, and they started with the video system, and today they have the compass, and together they made it a global system today. So when they started this presentation, they are down, they have moved up now. So regional systems, so we also thought, I think, I don't know, people would have heard that Kargil war, we had a problem, GPS signals were distorted, so that's why we lost all that. I don't know how the fact is that, but we also, because now we are putting so much applications are putting, and today we don't accept any car without your GPS navigation, right? Minimum you ask my car should have the GPS, I should drive without a problem. And when the applications are becoming so popular, and the Americans that GPS or anybody has got their capability to permit or not to permit signals over your country, or they have the capability of disturbing the signals and put into wrong system also. Then in ISRO, there was thinking was gone, and we also should have a navigation system, at least if not global, the regional basis, we should have our own system. So with that concept started, and we started working in ISRO, and we should not have a too, because it's but money, budget is a problem. We should have a reasonably low cost budget and able to solve at least mainland of India and around 1500 kilometers of Indian mainland. We should be able to navigate irrespective of GPS, GLONASS or Galileo or the video system. So that is the that concept. we started the regional navigation system. It's called IRNSS, Indian Regional Navigation Satellite System. And the Japanese also have got, because Japan, of course, I have not seen, but people say it's a big, huge, the huge skyscrapers will be there. And the cars of the traffic is moving and they are depending on the GPS signals. The signals will be blocked because satellites will be coming from all the sides. So you get blocked and you cannot get the 4 satellite signals. So you will lose the position. Then you don't know where to move. Take right turn or left turn. So they don't want that. They have started quasi-generic satellite system over Japanese. We will discuss that later. And these are all the regional systems. Even some more new operators are thinking, some countries are coming. They should have their own navigation systems that are going to come to that. And this is one part of having the satellites. And we talked about it going to give some sort of inaccuracies in the position. I want to improve the inaccuracies. These are all the augmentation. You augment for the satellite signals, you will get more accurate. You will get, I will talk later. But there are one of the systems, wide area augmentation systems by American of their own GPS system. So differential system by American, their own GPS system. All this they have that. So then M.Sc has built from the Japanese using the GPS system. These are all based on GPS. Best GPS satellites are required. These augmentation systems to work. And EGNOS Europeans also started. We have our own geo-augmented GPS satellite navigation. Where compared to the satellite signals of 20 meters, 30 meters what we are talking, I can go down to centimeter in 1 meter, 2 meters the type of I will show you the plots later. So these are the here we have the bugger system. Like this. Now let us look at the GPS system, which is very famous and all of you are familiar. And today we cannot move without this. So this is the satellite constellation they started. They have the 6 orbital planes A, B, C, D, E, F, and the satellites are phased like this. And you can see all that. The blue ones are the working satellites, and the light green are the space satellites. The satellites are moving. You have the across Earth. There are 6 planes. 55 degrees inclination. They will keep on moving. Why so? We discussed that dilution operation, all that. So plus also I will show you why we need it. So then the semi-major axis is 26561. That means 20,183.6 kilometers height. These satellites are placed in different orbital planes. Then they keep on moving. And eccentricity is normally 0. They maintain less than 0.0. Otherwise the satellites will be moving. And your x1, y1, z1 will become trouble. So to maintain that, I need to maintain these numbers. Next slide, please. Go to next. Now you see, as we discussed earlier, I want minimum 4 satellites to calculate my 4 unknowns, right? So that means now whatever the satellites, 27 satellites or 28 satellites GPS was talking, some of the satellites can get into the maintenance. And anywhere I am there, I should not lose the GPS signal. I should be able to complete my position and time. So that's how the constellation is designed such that the satellite is moving in such a orbits and separations. You can see this number will never go below 6. So fellow standing there, always we have a support of 6 or more satellites. So that's how everybody will compute and design his constellation, decide number of satellites and orbital planes, things like that. Thanks. Now it's not a simple system. They are very, very complicated. So even though my watch is giving me, or my mobile phone is giving, the things behind that are too many. So you have the space segment where all the satellites are there. Then you have the ground segment. You see there are all the things, they have the reference stations. Throughout the world they are deployed because the satellite has to be uploaded the data and frequently tell that what is your x1, y1, z1 or xi, yi, zi. To do that, the satellites will keep on moving. The stations will be telling them, yes, you are at this position, you are at this position. That data will be, satellite will be downlinking and receiver will be picking up. So for that you have the huge infrastructure, and you have the master control stations are there in the US, and they have ground antennas, the green triangles. Then Air Force launch stations also there. Alternate master control stations is there for them because they cannot depend on one thing like your New York tower. it cannot have a problem, then the whole system collapses. You need a backup plan, so there are backup plan. Then remote tracking stations are there. So NGM monitoring stations are there. So then they started with the GPS block 1. Then they gone to block 1, block 2, block 2R. Then they got block M. Then today block 3, 3 of like that, various satellites are bringing. And what is that they are trying to make is the system now, there are so many ground stations are there. Anywhere you have problem, that part you are having going to have some limiting problems with satellites. They don't want that. So when the satellites, new generation satellites are coming, they are trying to make it more and more autonomous. They are putting inter-satellite links, and one satellite even you don't need any of these stations. Entire thing they take out, and everything is controlled from the US itself. So that's how the next generation, the latest generation of the GPS satellites have come. And one is what we use on the ground. They have much more interest than this. They have two types of signals. One is what we get normal. There is other one is the precision code will be there. That is available only their own specific users or the military users. Because they go everywhere throughout the world. And anybody like you or me included will not be knowing where you are in ISIS or in the space or on the ground. So they need GPS aiding. So that's why they are global. And they want to make it more and more accurate. So that's why they are going to build the systems like this. Next. Next we will move on to the GLONASS. So almost the same time they started. Unfortunately, they could not do as good as the Americans have done. This system was not so popular because of the one is the other one is the CDMA. There is FDMA technology. This is the CDMA. They are not exactly compatible. Plus the number of satellites what they made also they are not able to sustain in the space. Continuously they never 19 satellites are required. So 24 satellites of that, 89 in new record they are not able to maintain. Even sometimes during 2005-6, even we are interacting whether we make the satellite reliable satellite and put their payload. Together we can make something like we made. But ultimately they decided they go on. And they have the 24 satellites in 8 satellites in each of the plane, 3 planes. Again essentially 0. Inclination is 64.8. Altitude is 19,100. Different from the GPS numerical system. And the orbital period is 11 of 15 minutes. Angular spacing between orbits is 120 because 3 planes 360 by 3 is 120 degrees. So this is how the Russians have designed their constellation to have a better computation at least wherever they are interested. Next please. So they also have the various constellations. Today they have got at GLONASS K2, GLONASS K2. Then GLONASS K we want to interact, we didn't go to that. Now they have come to K2. I think they are able to sustain and they are able to have their own position. And anywhere, any satellite map, if you see this is all the world over the GPS signals will be available. So this bottom numbers. So we can see this the best signals will be available. This and daily operation is increasing. Most of the time, world throughout the world they will try to give a reasonably good size, whatever 1 to 3 or 2 to 3 or like that, whatever numbers will come. This is how the dark numbers will look like, and they will put even today go to internet and click it. You will know your position, your place or any place, what is the GPS dot or the GLONASS dot or European satellite dot. Next, in our own dot. So then, as I told, the Europeans also thought they should have their own system. They started with the 3 GEO satellites. Basically, they started with the augmentation, that position accuracy in the GPS they started doing. They started with INSAT 3 GEO satellites with 15.5 degrees and 25 degrees and 21.5 degrees. They put 3 satellites and they started connecting like our Gaggan satellites. And then they thought they should make it global, and the 30 medium Earth orbit satellites were designed. So 9 satellites in each of the 3 orbital planes. So they call it a Walker constellation. 27 or 3. 3 space satellites will be there in each plane. One satellite will be there. Again, essentially 0. Inclination is 56 degrees. Altitude is slightly different from both of the American and Russians. 23,660. Orbital period is that. And Okay, ground equity representation. We don't have to worry because this is the today this constellation also full. They started the providing services. They have some open systems and they have the commercial service also. There, if you want more accuracy, you need to pay for the service and take it. So this also again, as I told, it's a complicated thing. They also have all the ground control stations throughout the city. They are all the places in the port. All are remote stations. They will link up to the communication networks and without any break they will be getting, and finally they will support the whole constellation, and you are supposed to get an error-free computation of the ground. So this is the satellite how it looks. Next. So Chinese, as I told, they started with a video system first with the geo satellites with the intelligence. And today they have a GEO, MEO and inclined geo orbits, all three places they have the satellites. They have right now 5 satellites in GEO at 36,000 kilometers, 27 satellites at medium Earth orbit, that is 27,876 kilometers with 55 times inclinations. 3 satellites in inclined geo. Somebody in the radio range, he can take that signal and he can compute that from the GPS, apply these corrections whatever coming from this transmitter, and he will get information. So this is called augmentation. So even though that much is varied, I am on dot here. You are applying from the corrections. This is real correction. So this is what the world or the EGNOS or M.Sc or the WGPS or the wide area GPS I talked all that for the So now look at it. The nominal GPS antenna position will keep on showing varying like that. When I apply these corrections and my stat of the position will be over a day, it will be something like this in meters both latitude and longitude. I am within this plus or minus 1 meters. That means I am getting correct position. Today, Delhi when trains are not able to move because of the fog. So many areas trains are delaying. You would have reading in the newspapers. I don't know how many of you have the habit of reading newspapers. I strongly recommend you should spend some at least 5-10 minutes to know what's happening. And aircraft you want to take off, it will not take off because the visibility is very poor. They need minimum visibility. Now once I provide this type of signals and I have a GPS receiver on board an aircraft, I don't need visibility. I believe my numbers and simply take off or land. I don't have to worry what is the fog condition or the dark or light is there, light is not there. I go with that. So this is how we generate augment. We make it in the other industries. It need not be aircraft. There are many applications. Next please. So what is that corrections? I have a GPS satellites. I think okay. I'll go to next slide and come back to this slide. That gives more visual. Now what is the system now? Augmentation system. You have the GPS satellites, any of 29 or 27 or 30 numbers will be keep on moving around there. They are providing signals. Some are visible, let's say 6 numbers are visible to over your receiver. Then I have those signals are got into the reference stations. The Indian reference stations, I am getting it. The like GPO signal what I called, General Post Office Bangalore. So these positions are fixed. So they will generate, they will use the GPS signals, compute the positions, they generate delta X, delta Y, delta Z. And here somewhere else also it is generating all these developments. This data will be executed. And we have the Indian Master Control Center at Kundanahalli, we have the station where all these reference stations data like something like 40 numbers throughout India, I showed where the stations are. All will be brought to the Mission Control Center in the Kundanahalli. From there, we compute the errors at the different locations of the world, India, where my interest. I will generate. I upload to the GSAT 10, GSAT 8, and one more GSAT 15 where we have the global payloads. They will receive the data and they will start transmitting next. Oh, okay. They will start transmitting. The aircraft is moving. It knows over Bangalore what corrections to apply. It needs to apply Bangalore correction. If it is at Trivandrum, it knows it is close to Trivandrum. It has to apply correction from Trivandrum. All corrections will apply. It will get exact position plus minus 1 to what I told. So these are all the places where our reference stations are fixed, their coordinates are fixed, and any difference is coming that is manifest in terms of errors. All the errors are brought to the Bangalore. Today we have one more master control center at Delhi as a backup, because Bangalore something happens, the Gagan payload cannot go haywire, and we have the parallel station at there. Next. So all this data from the Bangalore master control station we send it to the satellite. Satellite will send back signals over the coverage area, Indian land mass, plus where our aircrafts are flying. Next please. So this is the footprint of our antenna coverage of the GeoSat. So this many displaces, anywhere is there, he will get the correction signal, he will apply it, he gets position plus minus 1 meter, what I showed in the slide. So these are the augmentation is done. So now we have the GPS satellite, the reasonably accurate, and I want more accurate. I don't get the precision code, encrypted code, what I told is only for available for military people, and will not get a piece of information about that. I can still try to improve my position for my CAT-free applications like aircraft landing, takeoff, all that. I will do like this. So this is the Gagan system today in operational, and future whatever the aircraft, any aircraft buyer is aeroplane operator is going to procure. With this system, I am going to operate independent of the weather conditions. Next. So now what's happening worldwide? Everybody I told, Americans have got, the Europeans have got Techno system, we have the Gagan system, Japanese have got M.Sc. How they are going to put? So the VAS system, wide area accurate system, is done by the Americans. They basically interested in that place, but their satellites are available. This covering this, the GPS satellites, what I showed, available throughout their antenna campus are like this. Next please. This is Europe. Europe one there. They have the reference stations. So this much antenna footprint they are putting. Next. This country is from the Japanese M.Sc, the small country, but they generate the reference, and their antenna footprint is that. Next. So this is our Gagan. So in the latest in the augmentation system, we have 3 satellites covering this much area. Now let us assume world to this whole map is open, globe. So from the anywhere to anywhere, the aircraft is fitted with the augmentation receiver. It can seamlessly fly without any deviation. You don't have to, because any aircraft from here to Delhi you want to go, all the time the aircraft pilot should have a contact from the ground station. If he leaves here, somewhere in Hyderabad or Orissa or Madhya Pradesh, something you should have contact. Once the receiver, this augmented receiver is fitted with the aircraft, you don't need any ground control. I don't have to go zigzag to have my communication link with the nearby airport. So I can go directly the line of sight by saving the fuel, reducing the CO2 emissions. It will lead to lot of savings, safety. I don't have to worry about the fog conditions. I can go there. So today we have the system sitting in the space. Any aircraft fitted with the augmented receiver can fly seamlessly throughout the world. So now we come to what is that we are trying to do in India. We talked about the global systems. We told we are regional. What is that we are trying to do in India? If the resources are, we don't have the requirement of going and fighting in the Afghanistan, fighting in the Taiwan or in the South China Sea. We don't have that type of ambition. But we need our own requirements. But the GPS gives up. You cannot say that my car receiver cannot take me to my home. Still I need to drive my car because I so much use that I don't know which road to take. So for that we need to support that. Okay? So with that we have a space segment responsible for design, development and relation of the spacecraft bus systems. We have the payload to support the navigation signals. We have the ground segment, it's a huge segment, I will show you later. And the critical technologies, so we need atomic clock and precise measurement of the ground timing network, hydrogen image, sequence clocks, all that we need. Next. So now I told constellation design is very, very important, because what is my interest? Where to count my signals? I should meet my minimum designed or targeted requirement. Okay. I targeted what is my geometric and horizontal or vertical direction questions, type of orbit, number of satellites minimum I need for, and the satellite visibility over the place where I am interested, choice of geo and the geosynchronous, because there are two terms, probably Sundaramurthy would have told you. If I make inclination 0, it's GEO. If I make small inclination, the satellite moves as if moving like a 8. So depending on the more inclination, I make a big 8, the small inclination, small 8. I need a combination of GEO and GSO satellites. Impact of a particular orbital location, suppose I put a satellite, that satellite has some problem, what is the impact of overall position fixing? Orbital location availability. This is one more very important. Sundaramurthy or Nageshwara told you, this is very prime. Getting a house site in UVCE campus, not possible. I need to go beyond the Anantpur and the Vizag site. So like that, we are late entrance into the system. The whatever L1, L2 signals, the Americans, the Russians having, we don't have, because we also start transmitting there, we interfere. So they don't allow us to do that. So we have the orbital location and the frequency also a problem. We have chosen different frequencies, L5 and S5, and we are still doing the navigation. Next. So what is the ISRO Constellation? We, all this requirement, whatever I put, we thought we should have a 7 satellites, and with this particular configuration we are doing. So 3 satellites at the GEO. Today actually it is not GEO, we have a 5 degrees inclination. Minimum satellite at GEO is 5 degrees, because later they realized that if I make it 0, the Doppler shift will not be there. So for navigation position fixing, the satellite has to generate some Doppler. So we have made a 5 degrees inclination for the satellites. Then we have satellites at 55 and 100 targets. Okay, right. So 3 geostationary is not like GEO, it's the wrong thing. We have the 5 degrees inclination now. Other satellites are at 55 degrees, 29 degrees inclination. 4 satellites, go. So the satellites, of course, the ground user, if you say that they are moving like that, go. So all the satellites will keep on moving next. So they keep on moving, but actually there's another slide I mentioned that. So this geosynchronous at 5 degrees, that's the thing at 55 and 111 degrees, they will be going 29 degrees inclination. So this is how the whole system is realized now. So this is in place. We have the 3 orbital locations at 32.5 degrees, 55 degrees, 83 degrees, 11.5 and 129 point. So at 32.5 and 83 and 129 is 5 degrees inclination. And we have 2 satellites at 55 degrees and 2 satellites at 111.5 degrees. These 2 satellites will make a bigger 29 degrees inclination, and the others will be making a 5 degrees inclination. We have this is space segment. We have a whole lot of ground segments. We have the range and integrated monitoring stations, laser ranging stations to precisely know the satellite position. I told you your X, Y, Z has to be precise. If you do a laser ranging to the satellite, we have the retroreflectors on board the satellite. I can get a centimeter accuracy from the satellite. At 36 kilometer satellite, I can measure with the accuracy of centimeters. Less than 10 centimeters I can find out. We do a CDMA ranging stations to get a meter accuracy from the satellite. All that we do, and we are getting all this. We have a big navigation center controlling the whole network, and every continuously will be uploading the satellite data to the satellite because the satellite has to be updated. So this is a huge network, and we also have the timing network generating to the satellite as well as the ground users. All this is in place. Today we are able to provide next. So this is what we designed to provide the coverage. So this is India, and we are defined as a 2 zones. One is the primary service area where we get a better accurate signals, and we have our secondary service area. So over this entire area, anywhere the person is there with our NavIC receiving signal, the receiver, he can receive and fix his position. So primary area is 1500 kilometers over India. Then we have gone behind. All these signals are available over the secondary area. So with reasonably good accuracies, we can determine our positions. Next. So this is how the satellite looks. So I don't know, you would have seen some of the satellite pictures earlier presentations, both in remote sensing and communications. So this satellite is slightly different from that. So because the manifest is, as I told, we are limited by the budget and we have to be regional. Number of satellites has to be minimum and the satellite has to be small. It should be lifted to GEO orbit by PSLV rocket and it should sit in the small envelope of PSLV rocket. All that were done and I am the project director for this. So we have designed with a lot of iterations. Finally, this is the satellite. Whatever you are seeing, the circles are because of GPS navigation signal antenna, transmitting signals both in L5 and S bands. And we have the laser reflectors, talking the laser in the top corner of the reflector reflects anywhere you send a signal, it will come back in the same direction. And because the laser is the light speed and more accurately you can determine the position, there are various antennas. The top one is the fuel tank. The satellite will mass will be around 1425 kg, and in that 830 to 40 kg is the fuel. 600 kg is the satellite, full satellite with the payload and the bus systems. So these are tools from various. There are the star sensors because satellite will keep on moving. Anywhere satellite we should have to determine position. So we have star trackers and we have liquid electric motor because basically we put the satellite into 220 kilometers by 21,000 kilometers. But finally you have to take satellite to 36 kilometers. So we need a good amount of propulsion. We have the liquid electric motor, the water which is hanging, that's not the rocket engine. So we take satellite to the full 36 kilometers circular orbit. Next. So these are all the constraints. What we are supposed to do, it should be 1000 class satellite, configured for PSLV, navigation in L5 and S band because we don't have the luxury of L1 and L2 bands. CDMA ranging for the know the satellite position, corner view vector filters to improve the position accuracy of the satellite, repeating measurement frequency standard as atomic clock, dual helix array antenna, whatever antenna I showed for the transmission of the signals, hardware regulation of the extensive testing and qualification because total new systems are used for this navigation constellation. ISRO's experience both remote sensing and communication satellites are put to this to get an optimum combination of taking all the systems into consideration. So next generation also we started because the first generation 9 satellites we are in orbit. Of course, one satellite we could not put in orbit because of the PSLV didn't open up. The satellite got stuck in that. We lost that satellite. Otherwise, we have 8 satellites in orbit. And now we thought now we go to improve the signals because we also get into L1 so that we are globally compatible with GPS. So probably I don't know. The 4th year students are there. The coming modulation techniques we will study. So we call the BOP modulation, so binary offset coding. So somewhere the GPS is speaking up, they will not allow me to put my signal with the GPS signal. So offset by 5 MHz or 10 MHz, they call the binary offset coding. My signals will peak at the other places, minimum at the center 10. So that techniques were used and L1 signal also they are going to put in this next generation of satellites with the 2000 class satellites and we are going to fly as a Mark 2 satellite and we are going to have L1 addition to L5 and S band what already we are flying. Combination of propeller and delay down clock. Now we thought we should have our own clock and SAC Ahmedabad payload team has their clock and first clock we are going to fly in the coming months. And triple frequency array antenna because now we have the earlier we have L5 and S band, now we have L1, all 3 frequencies are combined and having a single antenna which will be transmitting all the 3 signals to the ground. Interoperability with other global navigation system we are going to ensure because we brought in L1. So now even it will not be it will transparent for you whether GPS is coming or not. Because we have L1, GPS watch is fixed with L1, this will receive from the airlines and we continue to give the position. You don't lose it. Next. So now we have a lot of challenges because first time we are handling such a precise atomic clock. Because I will explain the clock how it is, it's very critical. And managing the atomic clock, thermal, magnetic and microphonics is very sensitive, clock is very sensitive. And over a day, I should maintain a temperature at the base of the clock plus minus 1 degree centigrade at that orbital height. The satellite is up and moving, but I need to maintain, very able to do it. And the mission management, especially the satellite will be continuously, the satellite keep on moving. I should look at the 5 or 8 degrees latitude, the longitude is fixed. Always wherever satellite is moving, my satellite should manipulate both our planes and beam the signals there. So it is a continuously manipulating. Keep turnaround time for each satellite to achieve the constellation. Thermal control of high power TWT, we have a 250 watt S-band TWT. That is the highest power available today. And the accurate ranging of satellites, that's why CDMA we need to do, laser than we have to do. Hardware regulation production mode, because number of satellites are more, we need to have the backup plan. Enhance the autonomy in onboard satellite, because it should be satellite should be on its own. Should not ask it to keep on support from the ground. So it should manage on its own most of the functions. Next. So routine atomic clock, just I thought it will be interesting for you people, because you are the people who need to take up this type of challenge work, and you need to build a atomic clock for yourself. And you should fly and you get to enjoy that clock build. So I thought I would just explain to you what does it mean. We are talking so big about that. So atoms are characteristic translation frequencies depending on that. As I told, one or first orbit, second or third orbit, or the nth orbit. When the atom receives energy, it changes its energy state. So one state goes to the next higher state because it's excited, got more energy. This characteristic of rubidium atom is to in an atomic clock. The rubidium clock essentially consists of a voltage controlled crystal oscillator. I will show that. And it has got atoms in vapor cell occurs in 2 energy levels, F1, F1 and F2. Atoms are excited with light from rubidium resonance lamp at a higher energy level. So it can go to atoms will go from F1 to F2, and it cannot stay there, and it will come back. When it's coming back, whatever the extra energy from the higher state, lower state, has to dissipate. That is the what we get as the atomic signal. Go to next, please. So this is what the rubidium atomic clock and their energy levels go to. This is how the whole atomic clock is going to work. And all your electronic things are there. You have the voltage control crystal of VCXOs are there. You have the frequency synthesizers are there. You have the rubidium lamp and filters, vapor cell, microwave cavity is there, photodiodes are there, and the detectors are there. And you are doing the getting the 10 megahertz synthesized clock, accurate clock from the this whole transition, dynamic transition. One thing. Wait. So you see, this is how they excited. This is how you will get a transition. You will be measuring this threshold change and transitions. From there, you will get the frequency. That frequency you are synthesizing and getting 10 megahertz. This will be happening around 6.4 gigahertz. This transition because the electronic levels, rubidium clock, what I showed, the difference is something like when the higher state to lower state electron comes, till the energy gap is such that it will be around 6.4 gigahertz. It will transmit that 6.4 gigahertz. This frequency I will take it and connect it to VCXO. I do a frequency synthesis and get 10 megahertz accurate clock. Because I am doing it this atomic level, my transitions are perfect. I don't get into any of the every thing. Next one. So these are the satellites. So first, I don't know. This is I'm going to quickly show you the overall realization cycle of a particular satellite, the navigation satellite. Now I get a structure. I do a thermal implementation of the tanks and all the things. So then I basically propulsion system. I told out the 1425 kgs, my propulsion is 825 30 kgs. So I put the propulsion system in place, ensure that all the systems are in place, and because the tanks what we use, take it to 16.5 bar is our operating pressure, and we have the gas bottles. Okay, you can see the first slide, the left side, there is one black thing that's now we call gas bottle. That we keep it at 230 bars. So that high pressure, we need to pressurize and say that systems are safe because the 200 bar pressure something this building will not be there if you get close. So we have to contain that much. So with all that, 67 liter tank weighing 11 kgs. So then we go for the different panels. We put all the equipment into that and put the electrical interconnections. These are the power electronics packages coming to support various systems on the track. Next. So then we bring all the systems together, put as a single system. Then satellite goes into the tube chamber. we'll take it under vacuum, temperature extremes will take and test all systems are working including atomic clock. Then we bring it to clean room and we have solar panels, they will be stored and we need to demonstrate they are able to deploy and we do the deployment test. Then we measure the physical parameters like a center of gravity and moment of inertia on various missions. Then satellite we balance it. Then we do because it has to fly on the PSLV payload adapter will bring and do a fit check and say that everything is compatible. Both the rocket adapter and our satellite is compatible and we do the fit check. Then we take the satellite vibration test. We violently shake the satellite because when it's going through the rocket, it's going to undergo a lot of vibrations. Then we do a acoustic test because when the rocket is going during the 20 kilometers away standing, your window panels will be rattling when the rocket is going. Then assume that when you are in the satellite, so what will be the vibration mean your acoustic levels? Nominally, my voice may be around 80 dB what you are listening. Because the rocket produces something like 145 dB. So every 3 dB, the power will be doubling. Assume from 80 what we are listening to 145 dB what we are going. That is the type of acoustic load or noise the rocket is going to generate. That time the satellite should extend. So we put the acoustic chamber, we take it to the full frequency and power levels, ensure that everything is intact. Then we do a lot of electromagnetic interference and compatibility tests. Probably you have studied EMI/MC in your electronic courses. Then we do a radiation test. Now we have the antennas, and I am telling my coverage is like this, and I need to demonstrate the test. The way I want to radiate, my antennas are radiating, not radiating lower or more. I need to generate the antenna pattern. I do a radiation test in the compact antenna specifically. So then after that, my satellite period travel is over. I take satellite from Bangalore to the Devaraya for integrated with PSLV. Again, post on today's I need to ensure that all my pressure proton system is intact. I can take it 2.5 bars and 16.5 bars. Everything, all systems are working. Then I do one final deployment test. Then we drive in. Then we fill the propellant. Now the hazardous chemicals are being put to the satellite. Then we lose the access to the satellite. Final weighing we do. And we integrate with the PSLV rocket and we achieve 2 halves of the heat shield that is going to protect the satellite during the liftoff. Then we clear for the launch and we launch it. So this is the satellite starting from the end, done. I decided what I want to do. I want to do a navigation. So for that, what are the frequencies, what signals, what power levels, all that I computed. And I made a satellite and launched into the space. Then I start getting some signals from the side. I will try to maintain. Now having done that, what is that I am going to do it? Now the GPS is there. Who wants NavIC? So we have to take it. As I told, somewhere GPS is giving hand. You cannot sit in isolation. You said that the ISRO has given hand to us, so not protected. No, we don't want to do that. We want to safeguard your signals and your equipment. So we have a lot of chips are coming in. Mobiles are already started putting into that. On the left side, what are the small chips you are seeing? All that are mobile chips that are going to get into the mobiles and feature seamlessly. You don't know if GPS is coming or IRS is coming. So you will get a GPS is not there, you will continuously get your position. So you will keep driving, you don't stop that. So the right side things are bigger things and they are fitting into the bus. And earlier I remember I am coming from native place in Andhra. So bus timing they will say your bus is at 8:30. I go there, stand on the road and no communication, no, we don't know if the bus has gone or bus is coming, we don't know. Today I have the mobile, all the commercial equipment are by government mandate. They are having a NavIC based receiver, continuously they take the satellite signals, they transmit their position. So bus is coming, it exactly tells now the bus is at Guntur. The next station it has come. Another 5 minutes bus is going to come to the place where I am waiting. All that is available. Even my wife is traveling. Earlier I used to worry whether she has got the bus or not. But the phone only she says, now I can continue to track. And when the bus comes to Krishna, I take my car, go to switchboard and pick it up. So these are all possible because these chips are sitting in the receiver and we are able to do it. there is a government mandate, we have to use that, even the lorry, ship, all things will have it there. Let us look at some of the applications using this, what we are doing. Next please. Okay, now because the lecture is, the other lecture starts here, now because it is lecture named satellite navigation, then applications, now applications are very far. What are the things you can think of using this navigation signals for that? I want to do a precise farming. Unlike in India where you have the bullocks and doing all that. So you have the other countries, advanced countries you go, they do sowing with the machines. So the precisely they use the satellite signals from this and they will be dropping the seedlings and growing it. So for precise farming, agriculture is used. Next. So aviation, of course, as I told, we talk a lot about the aviation, how we can make use of the aviation. So next please. Entertainment. Suppose you have environment. Okay, sir. This somewhere fire is happening. Somebody rescue team has to go. You want to go precisely what's happening. Otherwise, you have to keep searching. So I can get my signals and get into the place quickly. Next. Marine. You know that you have high seas, you lost. You go deep inside, at least the coast, you will have that lighthouses. When you are inside, you don't have anything. You have the receiver, you know exactly, and how to move also you know. You put your path plan, you will move in like that. Next. Public safety, yes, somewhere something disaster happened. Today we are seeing somewhere in the Himachal something is happening. So we need to go to the rescue teams to go to. We should know that exactly what's happening there. So public safety will be addressed. Next. Disaster relief, yes, we need to access that place. Next. Recreation, okay, now you are going like this. You should know when all of you have to meet. So for that you need a precise position. So you have that, the space you are doing that, and you are exactly doing all this, your recreation, using your GPS, you go to the deep place. So you lose the track. So you have this GPS, you get into that. You correct location, come out. Otherwise you get lost. Railways also uses all the signals. Next. Roads and highways, we talked about the bus all that today, and even everybody is talking Bangalore also, all the BTS buses they want to fit and track each bus, how they are performing, where they are doing all that. Next. So highways also we need that. Then in fact in the space we use this, because the satellites are at 19,000 or 20,000 or 21,000. The space station has a GPS receiver. Even all our remote sensing, the other day you would have talked Raghavamurthy. We have the satellite positioning system. We get the satellite signal because the other satellites are higher. We have the receiver and antenna and receiver. We fix the position and we know what orbital height the satellite is there and what rate we are moving, because the rate information also I can derive as the position. All that will be done. And today, all this, even the Elon Musk SpaceX program, you heard and you have seen that of the spent stage, first stage always he will recover. Today he started recovering for heat shields also. So he has got the exact guiding mechanism using this GPS signal, and something like that, the ship's board is there, you put a plus mark, the stage will come and land on that plus mark. That is possible because we are using the satellite precise positioning signal and guiding and landing there. So even our own Space Capsule Recovery Experiment we launched in 2005 recorded 6, and we landed near to the Sierra and Bay of Bengal. We have a small GPS antenna and receiver and antenna. It transmits signal. You know that where the module has landed, we can go there and pick it up. Even the today ISS, International Space Station, we also can land in the SpaceX module, Dragon module. It transmits the position, and people will be nearby, won't pick it up. So that's the space also we use. Otherwise, spacecraft onboard also we use for its own position. Next. Surveying, earlier I remember as a boy in my village, some land if you buy, survey will come. And with 4 helpers, the big chain link to measure the yards and like that. Today all that is not there. We have a small device, put at 4 corners, get the coordinates, put into the mobile, come it will give you what is the area. And your all 4 directions, what is the length, all that will be done. It became so simple. and in the road laying everywhere for precise monitoring they ask GPS data. Suppose somebody contractor laid the road and 1.5 kilometers giving a bill to measure, we will ask, okay, you show me the signal. You put that to GPS to locations, give the signal, you can calculate and do it. It has come as simple as that. Next. Mapping, we can do that mapping next. And the timing, suppose you have so many grids. All the grids when you are doing, you are having a 58 transmission system and you have to add them in phase. Otherwise, if you don't add in phase, you will lose the things. So for that, you need to synchronize the grids. For that, how accurate your timing, more accurate, your synchronization is better. I think I don't have to tell you because we are electronic engineers. So we need the precise signals. They use the GPS timing for synchronizing the grids. Power grids. Defense. So the earlier days, World War I, World War II, you take more ammunition, drop more area. You don't know where you are dropping. So you dump simply. So that was the technology. Today there is not the technology. You carry small ammunition, precisely drop. I want to hit this building. I will gather coordinates of this window. I will give the program that window. The system will come and drop a small bomb. Otherwise, I need, wherever you want to full thing, I need a big bomb. Today that is not technology. Technology is, I know the precisely, I know what target I want to hit. I come precisely and at a small ammunition, I can hit it. So this extensively used in the defense. Today in our own missiles we are talking, the GPS general signal we use, the public signal what we are using we use. Or we are going to use our NavIC signal, we have today the other special signals for the special users. So we can also precisely guide our missiles and taking exactly the meter sectors, not centimeters. Next please. And it's not limited. So limited to your imagination, and you can imagine more applications, more things you can build, like mobile airport I was talking to you. So it is limited by imagination. You guys have got new ideas, looking at what is there, and you can make much more use. The signal is same, platform is same, your brain work and get more applications into the use using navigation signals. Okay, now as I told, our target is the first line, socio-economic development, protecting the people. How we are able to do it using these NavIC signals. Satellite rescue of seafaring fishermen with NavIC. So we have a small receiver and smartphone, so the simple smartphone Android phone is given to all the fishermen around the coast who are going to the fishing terminal, all the Kerala, all that Karnataka coast. They have a small NavIC chipset named a receiver sitting in front of this. And what's going to happen next? There is a Android application is developed, app is developed next. And now you see you have all languages. A particular person knows that particular language, so you are English or Kannada, you can select it, and you can get all these applications or updates will be coming on that next. So international boundary, because a lot of times you have seen newspapers would read Sri Lanka had caught the people, Pakistan had caught our fishermen like that. And now the fisherman is going beyond our border, it will start giving warning, so you are not supposed to go. So he knows that he cannot go and he has to limited by our border. Next, highway alerts, high waves alert will be given. There is a high, very rough weather, highway alert will be given, and the rough sea alert will be given. Tsunami warnings also will transmitting, and the user, the mobile immediately will know, he knows what to do and they will try to do it. So today, we are in combination with INSAT, we have the ocean satellite in orbit, and recently last launch we had one more ocean satellite, the biggest satellite. So that data will be getting a potential fishing zones, because the temperature of the sea, wherever the fish are more, the temperature will be slightly more than compared to other places. So we can map out areas, and this data will be go to this mobile, and he knows what will be the potential fishing zones. He can directly go there and fish it, not general. Next. So this is what the Vikram Sarabhai dream of taking satellite-based applications to the common man. We are happy today we can go to reach this level and try to do something. We can address the issues or problems of this fishermen. To that level, we are not with your mobile phone. We want to that level, and that too navigation signals are playing a role. Tracking and terrestrial movements, all this we have the combination of GSAT 6 with a big 6-meter unfurlable antenna and S-band signals and IRS providing navigation signals. We can track a particular ship built into that. The owner sitting in his office, you can see that what various ship, how it is doing, or a lorry, how it is moving, all that can be tracked today. So this is what we are doing, bus tracking or ship tracking, all that we are doing next. So one more thing we are trying to do is safety through SATCOM and SATNAV applications. I don't know, we can support about that or this, one more thing. Using same GSAT 6 and NavIC signals. We have this type of connectivity. Earlier, I used to remember more or less at least once or twice in a month. We used to get there is unmanned level crossing, some train hitting some people, some bullocks or some animals, all that is there. Today that has become much less because we have this type of satellite based system. NavIC receiver is fitted to the train, and near the unmanned level crossings there is a router. And we know that satellite what is the location of this particular unmanned level crossing coordinates, and when the train is coming, we continuously tracking it. And this hub and these intelligence, whatever the gateway they have this, they will keep on determining and say that the train is coming in 200 minutes or 100 minutes like that. They activate the rotor will start doing it. Both train and rotor will be doing it, so that persons are alert. They are not supposed to get into with all these things. And with this, we are able to avoid this type of unmanned level crossing problems area. And like this, as I told, more and more applications you can think. We have the communication satellites or the navigation signals are available, and unstopped we can do applications like this. Yeah, this concept is successfully demonstrated, and something like I was told 2,500 railway things are fitted with this type of receivers and the servicing. And now we are less listening about this unmanned level crossing, and much more applications are going to be developed. Now, I think this is the trends as I told. What's happening now? Is it end of that, or something is more is going to happen in the navigation field? Yes, definitely nothing is stopping. More global navigation satellite system will become operational. Even India from the regional, we are thinking we are going to slowly make it global, so that we have our mission make our presence everywhere, and we have our own signals. Interoperability will be a key cooperation mission among nations. That's why all these countries will be talking, making signals compatible. You have a receiver, more number of satellites are coming, and any satellite misbehaving also you don't become opaque for you, and it will be computing a position more accurately. Regional systems will upgrade to global systems. That's what I told IRS. They are thinking of going global. New regional navigation systems will be planning. South Korea is trying. Even United Arab Emirates, they also thought they should have a system that will come up. Wider acceptance and exploitation of navigation applications are going more and more. Same thing. They are going to find more applications. Internet of Things and location-based service are going to have more. Then satellites are going to do IoT of things. And for that you need something to happen in a particular car, you need a precise signal. So the navigation signal is going to aid that. Focus on the safety and security of navigation systems. We need to protect signals, we should not tamper. So we need good, rugged satellite signal system with all your encryption, all that techniques. More effects will be given to sub-centimeter and sub-mm augmentation systems. Today we are talking about 1 meter, and people want to make it more and more thing and make it sub-centimeter augmentation. Navigation satellite platforms will be used in multi-purpose mode because satellites are going around, and you have a global system. For example, American GPS or the Russian GLONASS for the battery change. They have an instrument for antenna, you can see that big Yagi type of antenna. The antenna is nothing but anywhere anybody nuclear explosion we do on the underground, it generates a lot of electromagnetic waves in a particular frequency band. So the antenna will be keep on. The satellites are available because 360 degrees on the globe, if there are some satellites always available, they will pick up that and yes, Pakistan is doing, or Iran is doing, or Iraq is doing. That type of other applications also going to be built on this, and the satellites are going to be multi-purpose because your presence is global, not like the geosatellites. Next, please. Yes, so you have this type of situations. So not to get into the trouble, options of navigation is you could be headed towards a chaos like this. You get into the trouble. So we don't want to get into that. So I have systems, and the honor is on you people. Now take it further and make it more, and find more thinking, more applications, and more money for you. Next, please. I think this is my last slide. Thank you for very much for patiently listening. I don't know how much I could convey, how much I don't know. I think at least some delta thing I could definitely give and use a glimpse of, because we talk in simply GPS, everybody, I have GPS, I'm going. But now you know what is the things involved, the complexity involved, the difficulties, what are the things of that. At least some part of that I can flavor, I can give it to you. Thank you very much for your patient listening. And again, I want to thank Nageshwar sir for including me part of this. Otherwise, sitting idling in the house. So this gives me some chance to test myself whether I can stand 2 hours here and talk to you guys. And thank you, sir, for giving me the opportunities, and for the students also for listening. Thank you very much. After I answer now, otherwise I can communicate with you later. Probably I have any questions. Sir, we can take some questions. How do you do it? So 5 o'clock. I told 5 o'clock. Because the signals are precise. Navigation signals. Yes, sir.
Thank you very much, sir, for this liberating presentation today on satellite-based navigation. And we never really thought that when we were looking at our So I think we will have a few questions now, and with your kind permission, sir.
Yes, sir.
I would like to do the topics.
Yeah, please. No, please. Please.
Anyone with a question?
Yeah, but I'll be in my office.
Any question?
So the question is, so even our satellites, what we have, those travel over the foreign regions. So how does this foreign region block the detection or the mechanism that whenever satellite pass through those nations, how do they avoid the detail so that the satellite doesn't take the detailing of those regions?
Okay, I understand your question. How do our signals interfere with others?
It's not like that. Let's say a foreign satellite which travels over our regions. How do we avoid such that it won't take the details of our region?
Details of our region, I don't think
Unless you use offense.
unless offense somebody want to do something, because they are all very well defined. Today I want to put a satellite somewhere. It is not just like that you can put it. So there is a international IQ form is there. You need to go there, register your location and your frequency, what we are going to operate, what type of application, all that we need to do. And then we continuously all these things will be tracked also. Somebody is doing some mischief, immediately will be given warning also. Today even Elon Musk is planning to go 1,000 plus satellites, and that satellite has inter-satellite training. Something comes, detects that, it try to automatically manipulate, it will not collide with that. All those systems are there. Non legally. Suppose somebody wants to do something and he can do it. Then the physical, because the satellites are, the positions are fixed. Now, for example, Nageshwar sir would have told, or Subrahmanyam would have told, we maintain the satellite within 0.1 degree field box. That means as long as that is there, it will not collide with any of the satellites. Moving away, we do the connection to the satellite in our propulsion system, we maintain that. As long as you maintain, you don't have the problem of hitting something. Otherwise, the space station at 350 kilometers is continuously moving. So many things are going up beyond that. The hit.
How do we protect ourselves when being spied upon?
No, that okay. That is only the open signals are there. For example, in this we have the two type of signals I told. One is for the common use, other one is for the special users. And the special user signals are encrypted. Even if you get it, you don't know what it is. So it's a product like WhatsApp. We say that all signals are encrypted. Nobody can decrypt it until you use the algorithm. Yes, sir. Please.
I just want to add in, I think your question got confused between navigation and remote sensing. That is my feeling. You are not doing a reconnaissance of an object moving in India by somebody else. You are trying to find out your location with respect to accurately, with respect to some reference point. Okay, you can use the Indian navigation system, IRNSS, NavIC, you can use it. You can find out your location. But reconnaissance is not the one which is the aim of NavIC.
No, reconnaissance we want to do it because we want to go to space. Because I want to take a picture of China Beijing. We cannot go by aircraft or take camera and do it. I can put a satellite and my satellite can command it. Take a picture, store it on board, come and play back for India.
We are taking pictures of
You cannot avoid.
Cannot avoid unless you directly by RF or laser or something they can do, which is not
You
legal.
can, that's why the advantage of satellite is you can go to a place where it's nominally not accessible. That is the idea of making a remote sensing satellite. I can take picture today what's happening in Gaza border. I can continuously monitor. We'll do that.
Wartime it is different. You can do many things.
Yes, please.
Yeah, anyone else with a question? Sir, I had a question. So, could you highlight the significance of the geo orbits for navigation purposes? And then, are there any efforts to optimize the payload in such a way that probably the same application could be achieved through MEO and LEO orbits because of the increased latency?
No, actually, okay. One is the latency is one thing. Basically, geo we have got the satellite, as I told, 4 satellites has to be visible. And I have put that slide. Our area is making the satellites, whatever I talked from 32 to 130 degrees we have put. Either the eastern part or western part or north or south, whatever the coverage area I showed, minimum 4 satellites has to be visible. So if I make any lower orbit, the satellites will be moving faster. It's not 24 hours orbit. So we cannot get the signals. The satellites run in. So only way is I put at 36 kilometers orbit. Orbital period is 24 hours. So that all the satellites overhead is all the time available. If I bring the orbit down, you need more number of satellites for doing that. Yes, you have the latency all that will come down, but the number of satellites will become more. You need more number of satellites. Your expense, your budget, everything is goes high. So that's how this particular constellation, whatever we are thinking, whether we can do it by taking satellites up and down with the 20 degrees inclination. So we are able to go up and north and south, and putting satellites from 32 to 132, we are able to provide that primary satellite coverage area with 7 satellites.
Geo essentially means it's a regional system. The regional system, our area is limited. We are shown in one slide, some 1,500 by 1,500. That is our area of interest. We have defined intentionally. So with respect to that, geo or near geo, GSO will meet the requirements and it is cost effective.
And if you want to go globally, I have to increase at least geo increase or more of the satellites like GPS or the Europeans or where more of the satellites, bring more planes.
Thank you.
Because the coverage is 100%. I want all the time, everywhere, anywhere, all the time we need the signals. We cannot afford to do it. That's
Yes, sir. Thank you, sir. That answered my question.